Alright, continuing with this series of videos, examining how physics is presented in university and such, and providing perhaps a alternative way of viewing the facts, the evidence, and such. So, something like cyclotrons and stuff were on or something. So continuing there. Moving charges in B fields. Moving charges in magnetic fields. Yes, B fields.
Because of the relativistic corrections that you see here with gamma, if you go to very high energies, then the time is not constant for a full rotation. So you have to adjust now the frequency with which you switch the potential between these gaps. So if the time increases, then this switching frequency has to go down, and we call those instruments synchrotrons or synchrocyclotrons. They have names. So you synchronize now and correct for relativistic effects.
You correct for the facts that it's hard to accelerate objects once you start getting them moving really fast. It's hard to add any more speed to them because of this fact that the matter is basically turning into a force. Matter is moving as fast as a force, it's turning into a force, is the real problem. And it's hard to push a force.
Modern accelerators have constant radii. They are rings. And so if you have a ring with constant radius, the only way that you can keep the particles in the ring when they have a low energy and when they have the high energy is by gradually increasing the magnetic field. So you start off with a weak magnetic field. You go around huge circles, very large radius, and you gradually increase the magnetic field as you keep accelerating them. And by making the magnetic field go up just in the right way, maybe all the way up to 2 Tesla, you can keep them in that ring.
And again, the key word is them. Because this really doesn't work on single protons or electrons. They're a stream, and as I'm pointing out, I think the logic is that the stream is pressurized. They all carry the same pressure they had when they were in atoms. The idea is there's energy trapped between them, and that is the energy that's really compressing. And so that's the that's their potential to keep going, essentially, is the fact that they're creating an internal pressure. They're storing the energy that you're putting in, and that allows them, like a spring, to use that energy when there might be a gap in that energy.
The first slide that I'd like to show you is the slide of an ancient cyclotron. It is actually a synchrocyclotron. It was built by Lawrence in Berkeley, and this was capable of accelerating protons to 730 MeV. You see here a person to give you a feeling for the size of this instrument. Lawrence received the Nobel Prize for
Can't really see the person, but anyway.
physics in 1939 for his invention of the cyclotron. The next slide is Fermilab near Chicago. This is one of these modern accelerators, they're also called sometimes colliders. And this has a diameter of 2.2 kilometers. And this instrument, this year, plans to accelerate protons up to 1,000 GeV. G stands for giga. Giga is the same as billion. So 1,000 giga electron volts would be 10 to the 12 electron volts. The beams of high-energy protons are made to collide with other nuclei to uncover the inner workings of nuclear physics. The higher the energy of the protons, the larger is the impact when the protons collide, and the more one expects to learn.
So again, they expect to learn something, but again, this breaking cars to understand how highways work, wouldn't make much sense. What you're going to find out is stuff that doesn't have anything to do with the real function. They're not the parts that are integral. Obviously the parts that are steering wheels, you need all this wheels and all this stuff on cars, but I just mean the idea of how the highways flow and how the traffic moves is so distant from this part of it. that this is almost superfluous, and it's so undetailed, smashed parts that we can't identify because we don't drive in cars, so we can't really know how they work. So it's not very useful information, in my opinion.
By using ever-increasing energies of the protons, which are nuclear bullets, one explores unknown territory. In the news, these
bullets, they're bullets when they want them to be, they're waves when they want them to be. They just keep making this stuff up, and it's not coherent. Bullet one day, wave the next.
Colliders are often called atom smashers. That is a flashier name which appeals more to the general public, who pays for all this with their tax money.
Yeah, we all know that, so I don't think you need to point that out in a physics lecture. Who pays for it?
This research is a multi-billion-dollar industry. The words atom smasher are actually a misnomer. The colliders smash nuclei, which are 10,000 times smaller than atoms.
Well, but technically the mass of the atom is the nucleus, so blah, 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 blah.
The next slide shows you the tunnel of the largest ring in the world, which is in Geneva, at CERN, which is a European collaboration. This tunnel, which already exists for many years, has a circumference of 17 miles. There's a radius of 4.3 kilometers. And in here are these protons being accelerated, of course under high vacuum. And with very modern techniques of superconducting magnets, they can even go up now to about 5 Tesla. And in this tunnel right now, a whole new experiment is under development, which is called the Large Hadron Collider, which is considered the holy grail for particle physicists. And it's hoped that that will go on the air in the year 2007 or so. And it will accelerate protons to an unprecedented energy. It will give them kinetic energies of 7,000 GeV, 7 times 10 to the 12 electron volts. Do you recognize me? Yes, I am Walter Lewin. And it's now 2013. A few months ago, the LHC made one of the most important discoveries in particles.
So again, his reading. Most important. Sorry. It's completely insignificant, completely meaningless, completely useless in understanding the basic functions of the universe. The Higgs boson. What has it done for us? What does it do for anybody who wants to understand how this energy flows through this system? It's useless in terms of understanding why a compass needle turns, why all this stuff happens. It's mush.
Physics of all times.
Yeah, of all times. No. This is complete propaganda crap.
One of the main objectives of the LHC was to prove or disprove the existence of the Higgs boson, which was already hypothesized about 45 years ago. The Higgs boson is part of what's called the standard model of particle physics, which is a set of rules.
Which is a set of incomprehensible particles doing who knows what, how. A bunch of completely undefined behaviors.
That lays out our understanding of the fundamental building blocks of the universe.
Again, it's just not fundamental. The fundamental is the electron and the proton. They're doing 99.9999999% of the universe's work. They're in the center of the sun, making the transition from one form of energy to another. They're doing all of the transformations of energy that we see and that we can possibly see happening in the universe. We can account for most everything that's happening with those two elemental bits. We don't need any of this crap.
And the LHC has discovered the Higgs boson. It has a mass of about 125 GeV. And there's little doubt in my mind that the Nobel Prize for this major discovery will be awarded very soon. Let's now go back to 2002.
Very exciting. Yes, and they probably read a similar paper for LIGO's bullshit.
So I would like to return to my overhead there so that you can see some of that what we just discussed. Right there, thank you, Tom. So here we have Fermilab. You see a radius of 1.1 kilometers. I showed you a picture from the air. And so they went up to 1.5 Tesla, so that's the maximum magnetic field strength. You get very close to the speed of light, by the way. And you see 500 GeV protons. And here you see the Holy Grail, the Large Hadron Collider, European collaboration in Geneva at CERN, whereby you have the circumference of 17 miles and the magnetic field that they hope to achieve going up to 5.5 Tesla using modern techniques of superconductors. So if you want to go around in these tunnels, by the way, you need a motorcycle. You can go 17 miles around. The goal of all this physics, of all these experiments, is to enter new territory, to learn about these mysterious nuclear forces, and to see what is inside protons and to see what is inside.
Right, and for what purpose? As the functions are all that really matters. What do they do? What they're made out of is not very. It's not going to be very informative because it's not going to really tell you how they do what they do. Frankly, and I don't think like I said, you haven't even got the clue where you have figured out that gravity is a real force. You haven't even figured out that push is more rational than pull. And you are worried about what these subatomic bits are made out of. You're just looking in all the wrong places.
Neutrons. And with these experiments, many nuclear particles were discovered whose existence was completely unknown previously. Now comes the issue, how can you see the results of these collisions, of these particles with very high energies? Well, you can make the tracks of these particles visible. In fact, today, you will see them with your own eyes.
You'll probably just see the common particles that we've always known about, electrons and protons in different configurations.
And in the old days, this was done...
Not going to see a Higgs boson, not going to see a gluon, not going to see any of this other stuff they say exists.
With cloud chambers, and that's the demonstration I will do today for you. But nowadays, they do them with bubble chambers. Let's first understand the principle. If you have a charged particle, whether it is an electron, or a proton, or an alpha particle is the nucleus of helium, 2 protons, 2 neutrons. If it goes through the air, it makes ions. And as it goes through the air and it makes ions, it slowly loses its kinetic energy. And it finally comes to a halt.
Right, it's going to do that whether it's hitting things or not. They just do that. They don't just keep going. That's the sort of the point, except for that, whatever, the helium nucleus. That can keep going.
If we take a 10 MeV electron in 1 atmosphere air, it could go 40 meters. If you take a proton of 10 MeV, it would only go 1 meter, because the density of ions is higher, because it has a higher mass. And if you take an alpha particle, which has a higher mass than a proton, and it has a double charge of a proton, then it would only go 10 centimeters. It's a very high density tracks that you would get from an alpha particle. And so one way you can see these tracks is using cloud chambers. And the cloud chamber works in principle as follows. You can just have a chamber in air, 1 atmosphere air, but you put liquid alcohol in there, that's the way we will do it, and you cool the bottom. You see one there, which you will see a little later. And you cool the bottom with solid CO2, and then you get inside this chamber, you get a temperature gradient. And there's a layer there where the alcohol should really condense into little drops, because it's that cold. But for reasons that are complicated, it doesn't do it quite yet. We call that undercooled alcohol. Even rain can be undercooled. Just below freezing point, it's still liquid. But the moment it hits the ground, it will immediately become solid, by the way. That's also undercooled liquid. Now here we deal with an undercooled vapor. And so when these ions are made by these charged particles, these ions act as seeds for the drops, in this case the alcohol drops. And you can literally, with your eyes, visually see these drops being formed.
And a lot of them. And, so clearly you're seeing something happening that isn't necessarily natural in the sense that you're forcing it through a medium and then you're seeing how the medium is affected by what it's doing. So you're not really seeing it in any sense. You're seeing the smoke of the train, not the train.
I'd like to go through one numerical example, and I want to go to a 500 keV electron, which you see there. Notice that I corrected the speed relativistically, otherwise you would get this ridiculous number that we calculated earlier, which is larger than the speed of light. And suppose we have a 1/10 Tesla field. Then the radius would be 2.9 centimeters. But after a while, this electron will lose its energy, and then there comes a time that it has only 100 kiloelectron volt left. By that time, the radius in a 1/10 Tesla field would now be 1.1 centimeters. And so when you look at cloud chambers, at the tracks of electrons, and you have magnets there, you will see the tracks being curled up, which of course is a result of the fact that the radius gets smaller in time, and since the magnetic field is constant, you can see then large radius here, and as the kinetic energy slowly decreases, the radius gets smaller.
Yeah, I think that happens even without a magnetic field, frankly, because I think I'm going back to like 6th grade, and I remember doing this little cloud chamber thing in science class. We all got a little bit of radioactive crap, and and I sort of remember I don't remember magnets, but whatever.
And smaller, and smaller. So let's look at a few more slides. In 1932, Anderson noticed a track in a cloud chamber which had the appearance of an electron. It had the right mass, it had the right charge, but the direction of curvature was wrong.
And the mass is dictated by the speed, so they don't know what they're looking at really. They're looking at smoke, and the smoke goes at a certain distance, and that tells them, it has to be a certain mass based on how far it goes. And that really has to do with how much voltage it has left and all these other questions. So it just has to do with whether it's behaving like a proton. It's not behaving like an electron. So instead of saying it's a weak proton, they decide to call it a positron. They decided to call it an anti-electron.
Concluded that it was an electron which was positively charged, which is now called the positron. And these positrons had been predicted on purely theoretical grounds by Dirac. And Anderson received the Nobel Prize for his discovery in 1936, only 4 years after he discovered the positron.
Again, discovered the fact that, you send some protons through lead and some of them come out weak. Wow, big surprise there.
And Dirac had already received his Nobel Prize in 1933 for his theoretical work. The bubble chamber is an advanced form of the cloud chamber. In the bubble chamber, liquid hydrogen is used, and if now the ions go through, the ions become the seeds now for little gas bubbles. So you have liquid, which really should have been gas, but it's not quite. And so now it forms gas bubbles. So in a cloud chamber, you're going to see the drops. In a bubble chamber, you see gas bubbles. But the idea is the same. And Glaser, who invented these chambers, is also from Berkeley, by the way. He got the Nobel Prize for that in 1960. So let's look at the discovery by Anderson. Here you see a positron coming from above. And this positron has 63 MeV kinetic energy, and Anderson put some half a centimeter of lead in there, which is very clever. Think about that. When it comes out, the energy now is less, because in the lead it produces a lot of ions, and so it loses a lot of kinetic energy, and it comes out with roughly 23 MeV.
Roughly. See, this is the thing. You don't know. The path for each proton can be different, and one can just be very unlucky.
And why did he do that? Because now he knows for sure that this particle came from above. Because when it loses energy, the radius is smaller. That's why he was sure that it was curved in the wrong direction. If you didn't have the lead, you never know whether the electron came this way, in which case the curvature would be perfect. But now he knows it comes from above, and if this had been an electron, it would have curved this way. So this is one of the early discovery, cloud chamber photographs by Anderson. The next slide is a bubble chamber, and you see here both a positron and an electron in a constant magnetic field. And it speaks for itself. Notice that the curvatures are exactly in opposite directions, and you see this spiral structure that I discussed with you as the electrons lose their energy. And since this is a bubble chamber, which has an enormous density, 1,000 times higher density, say, than air, these electrons don't travel 40 meters in these chambers. In air they would, but in this case it is substantially less, and so you can roll them up nicely. And you can study them, their momentum, and their charge.
What to say? Like I said, one thing hits, two things leave. They say antiparticle, particle, could be something else. Piece of proton, you know. But whatever, fine. Protons could be made out of pieces, like quarks, quark thing, you know. But instead, they'd have to do this antiparticle thing. That just, in my opinion, is a nonsensical notion for moving things.
Using accelerators and cloud chambers and bubble chambers, a whole new world of nuclear physics emerged. Wow. And between 1958 and 68, 30 new nuclear particles were discovered. And MIT has always...
30. That's just before, that's the 68. You know, now they're up to 100. Silly, made up, dopey, irrelevant particles.
Been on the forefront in this research. Professor Sam King, who's still at MIT, got the Nobel Prize in 1976. Steven Weinberg, a theoretician who did his work while he was at MIT, got his Nobel Prize in 1979. Jerry Friedman, still at MIT, and Henry Kendall got the Nobel Prize for their work in 1990. And Clifford Schul got his Nobel Prize in 1994. If I summarize the basic idea behind it, which is very relevant to 802, you accelerate these particles using electric fields. That's the only way you can accelerate them. Magnetic fields can only be used to confine them. It cannot change their kinetic energy. But
so again, says him. You know, I say obviously the coil idea is in a sense adding pressure because it's pushing a little bit forward. That's why solenoids move the iron in and out. But obviously it's a magnetic field that's moving the iron into the coil. It's accelerating it. So I think this is a garbage argument. I don't think there's any rule that you can't accelerate with magnetism.
Magnetic fields are crucial because that allows you, as you gradually increase their speed.
I mean, obviously you have to have a moving magnetic field to do that, and you can't move a magnet, okay, very easily. But you can move electricity very easily. So it's obviously there's always a connection between electricity and this electromagnetism being vital to making moving magnetic fields. But they're moving magnetic fields, they're not anything else.
To confine them, either by a ring, which is done nowadays, or in the old days, in these chambers of the cyclotrons and the synchrotron. And then we have the bubble chambers, in the old days the cloud chambers, whereby you use magnetic fields to get information on the radius of these particles as they are being detected. And out of all this emerged a whole new way of looking at our world and completely new ideas about what makes...
Yeah, completely confusing, messy, sloppy. Then they added multiverses and entanglement and all kinds of other rubbish, and it's just all rubbish. Doesn't have anything to do with the electron and the proton, which are the elemental bits, and everything kind of works based on their movement. They move, things happen. That's it.
The world tick. This is nothing short of a revolution. And so now I want to enjoy with you the last 5
minutes. It's a devolution. It's going nowhere. It's going the road to nowhere.
5 minutes of this lecture by looking at a cloud chamber and by looking at some of these tracks. You're going to see a lot of electrons in there. The walls of the cloud chamber are radioactive. just like you are radioactive. Your bones are radioactive, your windows are radioactive, they emit electrons, no protons, but they certainly emit electrons. And we have in there a radioactive isotope, a rod, which has thorium in it, which produces alpha particles. And so you're going to see electrons.
So it produces electrons and then some nucleuses.
Which make beautiful spider web structures. Please don't clean up yet, we have plenty of time. To be precise, we have 5 minutes and 18 seconds left. So these electrons, you will see them going like spiders through this chamber, and sometimes they change abrupt direction because they can collide, particularly when they have low energy, and then they push it off, so to speak. And then occasionally we may see an alpha particle coming from our radioactive thorium, and that makes a very thick track. And so let's try this. We have an expert here, which is Marcos, who has not only borrowed this instrument, and if you like it, we may actually buy it. It's not cheap, we may buy it. But he borrowed it specially for you, for which I'm very grateful, Marcos. And he also did quite a bit of work to get the light just right. It's not so easy to see those tracks. So Marcos, you will get a chance to adjust the lights if you want that. We're going to make it very dark. And let's enjoy then this wonderful world, invisible world of nuclear physics. So here you see this, the rod with thorium. So Marcos, feel free to adjust the light if you feel the need. I will go into the audience as well and see whether we can identify the electrons. Oh, there was an alpha particle. So this is this rod. And so the bottom of this chamber is cooled with solid CO2. Ah, there was an electron, very nice. As I said, you know, they almost look like spider web. There was an electron here. So also keep an eye on this rod, and occasionally you'll see a very dense track, which then indicates there was one. That's an alpha particle. There's a beautiful alpha particle. Just enjoy this. You know, you're looking at a world which is completely new. Think about it. You're looking at the world of nuclear physics. You're seeing individual electrons.
Well, you're really not seeing them again. You're just seeing the little puffs of smoke as they plowed along, you know, through something. What else is there to say? And you're only seeing the stuff that we've known about for a long time, electrons and protons, combinations of those things. And, you know, no Higgs bosons necessary.
And occasionally you see alpha particles. Here, there's one coming out. And think about the physics, what's going on here. This alcohol, which refuses to become drops. And then these ions say, we force you to become, well, here's an alpha particle. I don't know what it's doing there. So these ions force this alcohol vapor to become drops. It's an incredible complex picture that you're looking at. It is amazing every time I see this. It's absolutely fabulous. And all through these very simple rules. Let's think about it. We have the Lorentz force that makes these particles go around, electric fields that you can use them to accelerate them, and then this subtle way that you can actually make them visible, individual particles visible. It is a new world.
Oh, whatever. It seems kind of samey to me, but whatever.
And the goal of my lecture was to make you peek into this world, which has revolutionized our whole way of thinking. Thank you.
Yes, well, whatever. In a, I would argue, a bad way, not a good way. It's a bad revolution. Bad, bad. Bad scientists. Bad. Anyway, yes, this is not much to say. I mean, the standard model is convoluted mush, and I would argue just plainly irrelevant to most of physics and understanding the machine, this Rube Goldberg machine of reality. You just don't need these extra bits. They don't play a real role in the function. Alright, so till the next time. And such. That's it, really. I think so.